Hi everyone, let's talk about Demarva's formula for complex numbers. What it states is that if we have an alpha in the real numbers and we have an r, which is the magnitude in the positive reals, and alpha is the angle, and for all integers n, we have the following straightforward looking exponent rule for complex numbers: r times e to the I alpha to the power of n is equal to r to the n times e to the I n alpha. Now this might seem obvious and it might seem to be a straightforward exponent rule, but we have to look at its meaning to understand what it actually says. So recall that when we say e to the I theta, what it really means is cos theta plus I sine theta. That's the rectangular form of this complex number. So if we have r times that, it's r times this. So what Demarva says is that cos alpha, we're forgetting r for just a second, cos alpha plus I sine alpha to the power of n is equal to cos n alpha plus I times sine n alpha, which is actually pretty amazing because we're starting with an exponent and then it goes inside to where the arguments are. And there is a geometric meaning for it, but we're not going to worry about that too much. It just has to do with the fact that exponentiation is repeated multiplication, and multiplication of complex numbers involves a rotation. So there is a geometric meaning for this. So let's prove it, but before that we need a couple of lemmas. These lemmas follow from trigonometric identities since we're dealing with cosine and sine, but we're not going to prove them. We're just going to be using them to prove Demarva's rule. So the first thing is that r times e to the I alpha times s times e to the I beta, so we have two complex numbers, is equal to rs times e to the I alpha plus beta. So this is a standard exponent rule and you can use it, you can prove it using the addition identities for sine and cosine. The second rule has to do with negative exponents, and what it says is that r times e to the I alpha to the power of -1 is equal to 1 over r times e to the I negative alpha. Once again, that seems to be a fairly maybe even obvious exponent rule, and you can prove it using the Pythagorean identity and by sort of the complex version of rationalizing the denominator. I'll leave that to you as well. So let's prove Demarva's formula. What we're going to do is break it up into the cases where the exponent is n equals to 0, n is greater than or equal to 1, or n is less than or equal to -1. So just as a reminder, what we're trying to prove is that r e to the I alpha to the power of n is equal to r to the n times e to the I n alpha. And this has a trigonometric meaning in terms of the rectangular form of a complex number. So let's do n equals to 0 first. What we have is that r e to the I alpha to the power of 0 is simply equal to r to the 0. Well, it's a complex number to the power of 0, so it's equal to 1. And we can rewrite that as r to the 0 times cos of 0, which is equal to 1, plus I sine 0, which is equal to 0. And that is equal to r to the 0 times e to the I 0. And that's r to the 0 times e to the I 0 alpha. So we do have the equality that we want in this case. The case of n being greater than or equal to 1 is more interesting, and we're going to use induction. The base case is simple. We know that r e to the I alpha, base case is when n equals to 1, to the power of 1 is just equal to r e to the I alpha, and that's clearly equal to r to the 1 times e to the I times 1 alpha. So the base case holds, that's not a problem. Now for the induction hypothesis, suppose that for some n greater than or equal to 1, r times e to the I alpha to the power of n is equal to r to the n times e to the I n alpha. And what we're going to do is we're going to work on r e to the I alpha to the n plus 1, and that's equal to r e to the I alpha to the n times r e to the I alpha. So we've split up the n plus 1. And now what we get is that by the induction hypothesis, r to the n times e to the I n alpha times r times e to the I alpha, and that's equal to r to the n plus 1, and now we use the addition identity on these two components to get this is e to the I n alpha plus alpha, and that's equal to r to the n plus 1 times e to the I n plus 1 times alpha. And that's what we wanted, so that completes the induction. The last step is proving the Demarva's identity for n less than or equal to -1, so negative integers n. And what we'll do is that we'll use the positive version by setting m equals to -n, which is equivalent to n equals to -m. So we'll use whichever one of these is convenient. And what we get is that r e to the I alpha to the power of n is equal to r e to the I alpha to the power of -m, because n and m are negatives of each other. And that is equal to r e to the I alpha to the power of m, and then we're going to take that to the power of -1, since that exponent rule holds. Now m is positive, remember, so we can write this as r to the m times e to the I m alpha to the -1. And now recall what we stated before, our second lemma. This one over here. We're going to use that. So we're gonna take the reciprocal of the magnitude part and take the negative of the exponent part. So this is equal to r to the m -m times e to the I -m alpha, and that's just equal to r to the n times e to the I n alpha. So that proves Demarva's formula. Okay, so that takes care of all the cases. Thank you for watching, and I'll see you next time.